First of all, it's quite exciting to see everybody again, and welcome to today's Luohan Webinar. Today, we are super excited to introduce a new friend to you, Modibo Camara from Stanford GSB. So for those who haven't known Modibo already, he is a microeconomic theorist working mainly at the intersection of econ and computer science. Broadly speaking, so Modibo is gonna trying to bring the insight and perspective from computer science into how people make decisions under limited resources such as time or data. So in addition, he's also interested in how the data is gonna driven, how data is going to drive the regulations for people in order to adapt to the rapidly changing environment. So today, we are very excited to hear one of his talk in the series. So I promise you will learn a lot from today's talk. And without further ado, let me give the rest of time to Modibo.
Wonderful. Thank you. Thank you very much for the invitation first and for the lovely introduction. So glad to be here. I'll start by just giving you a few words about my general research interests, and then I'll dive into the talk. So most of my work is about bounded rationality. So thinking about situations where decision makers want to optimize, but their optimization is qualified by limited resources like time, memory, communication, data, etc. So part of my work is about building or developing foundational models of bounded rationality. And to that end, I largely use tools from computer science that, a field that really has sort of thought carefully about what are the resources that you need, again, time, memory, data, in order to solve a particular problem. Another line of my work is more focused on market failures driven by bounded rationality and how we can address those market failures through better design. So I try to develop mechanisms that are robust to forms of bounded rationality. I've applied some of these ideas to voting, thinking about how do we design electoral systems that provide voters with better incentives to become informed about the policies and candidates that they're asked to vote on. I've also applied some of these ideas to monopoly regulation, thinking about a setting where regulators and firms are in an unpredictable environment and have only limited and perfect data. How do you design regulations that will be effective even in that context? And then a lot of my sort of current ongoing interests are thinking about how to exploring bounded rationality and related market failures in other settings like AI and recommender systems. Okay, so with that summary, let me dive into what was at some point my job market paper. This is a project called Computationally Tractable Choice. So the starting point for this work are two observations. The first one is that people have only a limited amount of time in which to make decisions. That could be a few seconds, it could be a few days, it could be a few months, but there's always some limit. The second observation is that making good decisions can be time intensive. And this is something we learn from psychology, but it's also something we learn from computer science. So what I want to ask is, what are the implications of these two observations for behavior? Now, sort of a natural starting point is to look at the empirical evidence that we have. And by and large, I would characterize that empirical evidence as suggesting that people respond to limited time by using behavioral heuristics. Heuristics are simple rules that we use to make complex decisions quickly. An example of a heuristic that will be particularly important in this talk is called choice bracketing. So choice bracketing roughly says that when a decision maker faces multiple different decisions, she will make each decision without considering the rest. And this is something that has widespread empirical support both in the lab and in the field. So let me begin with an example of choice bracketing. And then I want to try to take a computational perspective to that example. So the example comes from a 2007 AER paper by Ferl and Goethe. These two authors are running a field experiment, and they work with two companies in Switzerland that employ bike messengers. So bike messengers are delivering letters or small parcels from one part of a city to another. Now, in these companies, what happens is bike messengers the employees are signing up for daily shifts of 5 hours, and then they get compensated per delivery that they complete. So in particular, bike messengers that put in more effort, that like pedal their bike faster, could earn more money. Now, what the authors do is they increase the wages that the bike messengers are paid per delivery. And interestingly, what they find is that when they increase the wages, the bike messengers actually put in less effort per shift. Right. So this is perhaps odd, right? You might have thought that, okay, if I'm getting paid more per delivery on Monday and less per delivery on Tuesday, what I want to do is I want to, pedal my bike faster, put in more effort on Monday, get more money out of it, and then consume more leisure on Tuesday. But that's exactly the opposite of the pattern that we see in this field experiment. So how do the authors explain this? Well, they suggest and they provide some additional evidence for the idea that what the bike messengers are doing is they're using a daily income target, right? So this is like, I want to earn $300 on a given day, and I'm going to pedal my bike just quickly enough to earn that $300. Now, if I get paid more per delivery, I don't need to pedal my bike as quickly in order to hit that threshold. So what's interesting here is not so much that there's an income target per se. What's interesting is that the bike messenger, that the target is daily. The bike messengers are sort of thinking, planning one day at a time. They're not thinking about Tuesday when they're optimizing on Monday. So let's see if we can understand this from a computational perspective. Let's make the example a little bit more concrete. So let's suppose that we have a worker, and on any given day I, the worker is going to choose whether to put in high effort or low effort. Let's suppose that there are n days in total, and xi is going to denote the effort decision on day I. Now, one kind of behavior that the worker could engage in, as suggested by the previous paper, is the worker could plan one day at a time. And one algorithm that the worker could use to plan one day at a time is to simply search over the two actions, high effort or low effort, for every given day, and then repeat this for all n days. Now, the amount of time it will take for this algorithm to deliver a choice will be growing linearly in the number of days. And we're going to think about linear time algorithms as being plausible, in the sense that this is a plausible description of the a plausible way to generate the behavior of planning one day at a time. Now, another kind of behavior that we could imagine the worker engaging in is what we would sort of more classically assume in an economic model, that the worker is planning n days at once, right? So they're thinking about Tuesday, Thursday, Wednesday, Friday when they're optimizing on Monday. Now, one algorithm that we could imagine the worker using to plan n days at once is to simply search over all the vectors x, where again, x is going to be this vector that describes on every given day, are you putting in high effort or low effort? Now, there are 2 to the n such vectors. And so this algorithm, which searches over all these vectors, will take an amount of time that is growing exponentially in the number of days. And exponential growth, of course, is extremely aggressive. So we're going to think about this as not being plausible, right? So even if the worker had the computational processing ability of a modern computer, rather quickly as you increase the number of days, the amount of time taken for this algorithm to deliver a choice would exceed the lifespan of the worker, right? So in that sense, it's not a plausible description of the way that the worker makes decisions. But we want to be careful, right? So it's not obvious whether there exists a quicker algorithm that maybe takes advantage of some structure of the problem to plan n days at once in faster than exponential time. So we don't want to yet say that planning n days at once is not a plausible behavior, but what I'm going to say is that searching over all the vectors x is not plausible. So this example is going to motivate or suggest my research question and motivate the way that I address that question. So the research question that I'm asking is whether behavioral heuristics are necessary responses to computational constraints. And the way that I'll model computational constraints is I'll ask whether there exists a relatively quick algorithm that generates the hypothesized choices, right? So relatively quick, meaning something like linear time or more generally polynomial time, rather than something that takes exponential time.
Sorry, Modibo, can I quickly cut in and ask a question?
Absolutely.
Yeah, so the assumption that you have there is that the worker do not have the ability to make all the choices considering all the days, right? It will exceed the lifespan of the worker, right? I'm curious that when you make choice, it might be sequential. So once you make a choice for day one, that might, facilitate your choice in day two. So somehow, I think the implicit assumption that you have here is that all the choices are independent, basically. And somehow that, the time you need to make the next choice just grows or expands exponentially. So that's a rather strong assumption, I would say.
So I want to make sure I understood you correctly, but let me say something. So what I will say first of all is that you can certainly imagine, the worker following some behavior, making some choices that look sort of sequential, right? Like you make a decision on Monday, and then on Tuesday, you take into account the decision you made on Monday in order to on Tuesday, right? And in fact, that kind of behavior where I'm not necessarily thinking about Tuesday, Wednesday, Thursday, Friday when I'm optimizing on Monday, but when I'm optimizing on Tuesday, I'm thinking about Monday. When I'm optimizing on Wednesday, I'm thinking about Tuesday and Monday. That sort of behavior will actually come up towards the very end of the talk. So we'll discuss that more.
Right.
But yeah, so I don't mean to rule out that kind of behavior. But the point that I'm trying to make is that if on Monday, I'm trying to take into account Tuesday, Wednesday, Thursday, Friday, and on Tuesday, I'm taking into account Monday, Wednesday, Thursday, Friday, and on Wednesday, I'm taking into account Monday, Tuesday, Thursday, Friday, the amount of things that I need to take into account will be growing quite quickly with a number of days. And at least the most obvious algorithm that you could imagine is going to be quite slow. Does that answer the question? If not, please let me know.
Yeah, it does, but I'm still a bit confused that in the sense, once you've made decision, that's done, right? So when you move to next day, so what's been done on day one, that's passed. So then I only have to take account day 3, day 4, and day 5.
Well, it depends. I mean, so if optimality means you need to make the right decision on the first day, then you can't ignore the fact that the first day might not have been made optimally.
Okay, right, that sense. Okay.
Yeah. But also, I hope when I introduce the model, it'll become a bit clearer as well.
Yeah. Right. Thank you.
Thank you, and please, chime in with questions at any point. Okay, cool. So this is an example. Let me be a little bit more precise about the framework and the main results. So the key definition in the paper is this idea of computationally tractable choices. So I'm going to say that choices are computationally tractable if there exists some algorithm that generates those choices in a most polynomial time. Now, to be clear, this is intended to be a conservative definition, right? So I'm really only trying to rule out the behaviors that we're pretty confident are fundamentally hard to exhibit in a reasonable amount of time. I want to emphasize that there are many choices, things like, maybe not choices, but behaviors like adding two large numbers together that can be done in, say, linear time, but are going to be challenging practice for humans, right? So what I'm trying to do is I'm trying to say, okay, well, suppose that we really only take away the things that are the very hardest things. What can we say in that context? And it turns out we can say quite a bit. So I'm going to have two set of results. My first set of results will argue that under standard assumptions, behavioral heuristics are necessary responses to computational constraints. More precisely, my first three theorems will show that if choices are computationally tractable and they satisfy the expected utility axioms of von Neumann and Morgenstern, then they're observationally equivalent to forms of choice bracketing. Okay, so we start with a very sort of standard notion of expected utility maximization. We add in computational tractability, and all of a sudden, the only kinds of behaviors that are remaining in the model are ones that look like this heuristic that we discussed in the previous slides. So that's the first set of results. But at this point, it makes sense to take a step back and ask whether these standard rationality assumptions, so the expected utility axioms, whether they still make sense, whether they're still appealing in the context of computational constraints. And what I'm going to argue is that given computational constraints, those standard rationality assumptions are not always normatively appealing. Let me be a bit more precise. In my fourth theorem, what I'll show is that for a decision maker that intrinsically wants to maximize the expected value of some objective function, there may exist heuristics that will violate the expected utility axioms, but perform better than any tractable choices that are consistent with those axioms. So in other words, if you're computationally constrained, as I believe we are, then you might be better off making decisions that an outside observer looking at those choices would say, this violates this axiom, this is not rational, etc. Okay, so that's the framework, main results. Let me know if there are any questions at this point. Otherwise, I'll touch briefly on related literature, and then we'll get into the model. Okay, related literature. So, of course, this is related to a large body of work on bounded rationality. Much of this work, certainly not all, relies on more restrictive computational models than the one that I'm going to be using. So you might have heard of like finite automata being used in economic models. Finite automata are a special case of the more general model of a Turing machine that I'm going to be relying on here. The benefit of using a more general computational model is that when I impose a tractability assumption, that is a weaker assumption. There is perhaps the most closely related paper to mine is a paper by Federico Echenique and some co-authors that looks at a very similar notion of computational tractability, applies it to a very sort of classical model of consumer choice with budget constraints, and shows that in that setting, according to their definition, any rationalizable choices are also tractable. So in other words, in that context, tractability has no bite. It has no implications for choice beyond rationalizability. What I'm going to show is that in my setting, where you're thinking about a setting with choice under risk, tractability has very strong implications for choice. What I'm doing is, of course, also very much related to the subfield of economics and computation, thinking about tools like computational complexity theory and what they can tell us about economic phenomena. And then, of course, this is related to a lot of work on narrow framing heuristics. The idea I'm sort of focusing on a few things at a time. Narrow framing heuristics include choice bracketing. There's theoretical work that motivates narrow framing through models of rational inattention, through axiomatic models of decision theory that don't look at computation. And then, of course, there's a large body of empirical work that studies choice bracketing and related heuristics. All right, so
Can I ask a question?
please, yeah.
I'm wondering why is that in your literature review, one paper says the tractability has no implication for classic consumer theory. What does it mean?
What does it mean, you said?
Yeah.
Yes.
Why is no implication, no relation?
Yeah, so the definition they use is slightly different than mine, but I'm going to ignore that technical point for a moment. Basically, what they're showing is that if you're a consumer, you're buying some bundle of products, and you have no uncertainty, and you have a standard linear budget constraint, then any rationalizable choices can be rationalized by a utility function that's easy to optimize, right? Easy in the sense of polynomial type. The setting that I'm looking at introduces, in particular, it's going to introduce risk. It's going to introduce uncertainty. And so what I'm going to show is that when you have uncertainty, that result does not hold, right? So when you have uncertainty, there are many utility functions that are rationalizable that are hard to optimize in polynomial type. Does that clarify?
Yeah, thank you. I understand.
Yeah, also great paper to take a look at if anyone's interested. All right. So let me outline the talk. So I'm going to start with the model, give you about 4 slides related to the decision theoretic model, and then 2 or 3 slides on computation. Then I will dive into the first set of results relating choice bracketing with tractability. Then I will move on to the second set of results that revisit the normative appeal of the rationality axioms. I'm going to skip the proof sketch for today in the interest of time, and then I will conclude. I'll try to leave about 10 minutes for questions at the end. All right, so let's dive into the model. So in the model, we have a decision maker. The decision maker cares about something. What is that something? It's an outcome. I'm going to denote an outcome by X, and it's going to belong to some set script X. Now, before I tell you in more technical detail what the set script X is, let me give you some examples of things that I want to capture here, okay? So you might want to think about the outcome X as a consumption bundle, right? Where Xi is the quantity consumed of good I. Or you might want to think about X as the income from some investment portfolio, where Xi is the income earned from asset I. Now, what I want to highlight about both of these examples is that the outcome is likely to be very high dimensional, right? So think about you're a consumer in a grocery store. There are like tens of thousands of products in the typical grocery store. And so the consumption bundle would have to sort of indicate for each of those products, how many units you purchase. Likewise, for an investment portfolio, if you are a trader on the New York Stock Exchange, there are almost 3,000 different firms listed on that exchange. And so your portfolio is going to be, on the order of 1,000 dimension. Okay, so what I want to do is I want to capture the sense in which the outcome might be this very high dimensional object. And particularly, I want to capture the sense in which the outcome might be an arbitrarily high dimensional object. But still, always think of it as a finite dimensional object. The way that I'm going to do this is by letting the set of outcomes, X, consist of eventually zero sequences. So more precisely, I'm going to think about X as a sequence of rational numbers where there exists some n, some number n, such that the first n coordinates of X can take on whatever value, but then coordinates n plus 1 and onwards are zeroed out. So what does this mean? It means that the outcome X is effectively n-dimensional. And this device is going to allow me to talk about n-dimensional outcomes for arbitrarily large n, but always finite n. Okay, so those are outcomes. Next, let me talk about choices. So again, think about yourself as an investor, right? When you're an investor, you don't get to choose the income you earn from each asset. What you get to choose is like the number of shares that you buy from a given firm, which will be linked in some stochastic sense to the income that you earn. The way that we'll model this is we'll think about the decision maker as choosing lotteries. So decision maker will choose a lottery, which is just a random outcome, right? More formally, it's going to be a map from the unit interval sample space into the space of outcomes. You can think about the unit interval as just being like the outcome of a random number generator. We can also think about lotteries in the following way. We can think about them as random vectors, X. Again, outcomes are high dimensional, and so lotteries are also high dimensional. They're high dimensional random vectors. Each random variable that constitutes one coordinate of that random vector, I'm going to call a partial lottery. So maybe X1 represents the random earnings from Apple, X2 represents the random earnings from Alibaba. And in particular, you might think about those earnings as being correlated across different assets. Okay, so the decision maker is going to be presented with a menu, M, that is just a finite set of lotteries that they can choose from. And we're going to have some collection script M of menus that represents the universe of menus that the decision maker might be presented with. And then finally, we'll have a choice correspondence, C. The choice correspondence is going to map menus in the collection of menus to lotteries within that menu. Okay, again, let me know if there are any questions. Otherwise, what I'm going to do next is I'm going to tell you, one, a little bit more about this collection of menus. And two, I'm going to tell you what is the rationality assumption that we're going to impose on the choice correspondence. And then we'll move on to computation. So let's start with menus. A common assumption that I will also make is that the collection of menus includes all binary menus, right? So in other words, a menu with at most two lotteries, X and X prime. The idea is these are simple kinds of menus, and if presented with such a menu, we might expect the decision maker to be able to make a decision. Now, this is not going to be quite enough for my setting, and the reason is because we want to think about the decision maker not just as making binary decisions, but we explicitly want to think of them as making many different decisions, right? This is the sort of high-dimensional aspect of the problem, the sort of the feature of choice bracketing, which is like I'm making many decisions and having to decide which ones to focus on at a given time. So to capture that, I'm going to make another assumption, which I think of it as like the natural extension of this more standard assumption. And the extension is that I'm going to assume the collection of menus includes all, let me rephrase that. The decision maker might be presented with menus that look like making many different binary decisions. So let me be a bit more precise about what that is. To do that, I'll need to introduce 2 bits of terminology. So first of all, I'm going to define a partial menu, MI. A partial menu is a set of partial lotteries, XI. Again, partial lotteries are just one component of the random vector that is a lottery. You could think about partial menu as indicating, like, how many Apple shares I'm allowed to buy. Then we can define a product menu, M. And a product menu is simply the Cartesian product of partial menus. The defining aspect of a product menu is that what I choose in dimension I does not affect what is feasible in dimension J. And with these 2 bits of terminology, I can state my assumption more precisely. So I'm going to assume that the collection of menus includes all product menus with binary partial menus. And again, this is just my way of formalizing the idea that the decision maker might be presented with many different binary decisions. Now, of course, this is a richness assumption, right? I'm not saying that the collection of menus includes only product menus. You could add in other kinds of menus in there as well. And the hardness results that I would have would just get potentially stronger. So those are menus. And then next, let me define the rationality assumption that I'm going to impose. So I'm going to say that choices C are rational if they can be rationalized by preferences that satisfy the expected utility axioms. Or, more precisely, if there exists a utility function U mapping outcomes to real numbers such that the choice that the decision maker makes is always the lottery that maximizes expected utility within the menu. Now, note, as usual, this is an as-if definition. So I'm not saying the utility function at this point represents anything intrinsic about the decision maker. I'm just saying that this is a utility function that rationalizes the choices that are made. All right. So now we can move on to computation. All right, I'm going to start with sort of a simple diagram to illustrate what I mean by choice as computation. Let's suppose that you are in a restaurant and the waiter hands you a wine list, and your choice problem is to choose a wine. Now, the wine list is, some document written in some language, indicating the wines that are available and the prices at which they're available. Now, you receive this wine list, and what happens? Well, you undergo some kind of mental process. And after undergoing that mental process, you output a description of the wine to the waiter. Now, one way to think about what I'm doing here is I am using the computational model of a Turing machine as a model of the mental process that the decision maker is undergoing between receiving the wine list and picking a wine. And the nice thing about the computational model of the Turing machine is that it's very general, right? And it's thought to be applicable to a wide range of phenomena, even going beyond digital computers. Now, I won't go into too much detail on what a Turing machine is, but you can formally justify yourself as thinking about the Turing machine as just a program written in your favorite programming language, Java, Python, what have you. I'm going to give a different interpretation of the tractability assumption that doesn't rely on the idea that mental processes can be simulated by computers in about 2 slides. Although if you're happy with that interpretation, I personally am, so that's good. Okay, so that's the high-level idea of choices computation. Now let me be a bit more precise about the computational tractability assumption. So I'm going to say that choices are tractable if there exists an algorithm A that does 2 things. First, it takes in a description of some menu M, and it outputs the choice that the decision maker would have made from that menu. Second, the algorithm is going to halt in a number of steps that's growing at most polynomially in n, where n is, say, the number of products in the grocery store or the number of assets that you can invest in. Now, this is an informal definition in a couple of senses. So if you'd like me to be more precise about anything, or if you have any questions, just let me know. Again, the idea here is that we're really trying to be conservative in the sense that we're only imposing a relatively mild computational constraint. Certainly, there are things that can be done in polynomial time that would be hard for people in practice, but I'm going to sort of be conservative in the sense that I'm not excluding those from the definition of tractability. Okay, so let me make two quick comments, three quick comments. First one is that rationality and tractability are both positive properties of choice correspondences, right? So rationality says there exists some utility function that rationalizes your behavior. It doesn't say that this is the true utility function, whatever that means. And similarly, tractability is also sort of an as-if property. It says there exists some algorithm that could have generated your choices quickly. It's not saying that this is literally the algorithm that you are using. Now, my first three theorems, my first set of results, will ask when are these two properties compatible? And then my final result will ask a given tractability, is rationality still desirable? All right. So before we move on to the results, let me just briefly mention one thing that's going to be important to the analysis. And this one thing is called computational hardness conjectures. So in computational complexity theory, the part of computer science that I'm sort of applying here, many of the results that are shown are based on unproven conjectures that are nonetheless thought to be true. So the most famous of these, which you might have heard of, is P not equal to NP. P not equal to NP essentially says, so it refers to a set of problems, set of computational problems, for which we don't have any quick algorithms. And for which we've been trying to develop quick algorithms for many, many decades and haven't been able to. For which if we could come up with quick algorithms, not the person who came up with a quick algorithm for them would generate a lot of fame for themselves and probably a lot of money as well. For which, if we could find a quick algorithm for any one of these problems, we could find a quick algorithm for all the rest. Okay? So these are problems that, again, we've been trying, and we've had very powerful incentives to make progress on, and yet we haven't really made that much progress. And so the P not equal to NP conjecture essentially says that the reason why we haven't made any progress is because these problems are fundamentally hard. There simply do not exist any quick algorithms. Now, you'll notice that there are three conjectures that I've written here, indicated by different numbers of asterisks. The more asterisks, the stronger the conjecture, but they're all of the similar flavor as P not equal to NP. Now, before I move on, let me sort of get back to one thing that I promised I would say, which is what happens if you don't like the interpretation of the Turing machine as sort of a model that is rich enough to capture whatever physical processes going on in your brain. Well, an alternative interpretation of the results in this paper are the following. Suppose that you could find me a decision maker that is capable of making choices that maximize expected utility according to a utility function that I'm going to call intractable. Well, then this person, let's suppose you're that person, right? What my paper does is it shows you how to convert your choices into a quick solution to these problems that I referred to that are thought of as being very hard, right? So again, if you could make choices according to an intractable utility function, then you would have a practical method for solving these thought to be fundamentally hard problems. And you would probably be very famous, and I would probably be very famous, and everything would be great. I don't think that's the case. I don't think that's possible. And if you don't believe that's going to be the case, then you can hopefully believe the results of this paper. All right. So that's it for the model. Next, what I want to do is I want to dive into the first set of results. Again, any questions about the model, please feel free to ask. So the first set of results are going to be linking choice bracketing to computational tractability. If we think about this blank slide as corresponding to the set of all choice correspondences, we can depict the set of all rational choice correspondences in blue, and then we can depict the set of all tractable choice correspondences in red. This purple section at the intersection represents a set of rational and tractable choice correspondences. And so our first goal, the goal for the first set of results, is to characterize that intersection. When is rationality compatible with tractability? Now, I do characterize the entire intersection, but to start with, what I want to do is I want to give you sort of a simpler result that adds an additional assumption. That assumption is symmetry, and then characterizes the intersection of rationality, tractability, and symmetry. So that's where we're going to start. It turns out that this intersection looks like narrow choice bracketing, this heuristic that I mentioned earlier on, or equivalently, it looks like a choice that can be rationalized by an additively separable utility function. So let me be more precise and further about what symmetry is. So I'm going to say that a utility function U is symmetric if the arguments are interchangeable. So in other words, if I switch xi with xj and xj with xi, utility does not change. Now, this is a perhaps reasonable assumption in some settings and a terrible assumption in others. So for example, in consumer choice, it is a terrible assumption, right? Because what this is saying is that I am indifferent between 1 apple and 0 bananas and 0 apples and 1 banana, right? Which generally is unlikely to be true. So this is not a great assumption for many applications. For some, like investment, you might think of it as a reasonable assumption. What this says is that the money that I earn from Tesla is interchangeable with the money that I earn from Microsoft. In any case, aside from whether this is an appealing assumption for a particular application, it's a convenient starting point for me to give you sort of a special case of my more general result that's a little bit easier to interpret. So let's make an assumption, which is that sort of weakest computational hardness conjecture, P not equal to NP. And given that assumption, my theorem 1 is going to say that if choices C are rational, tractable, and symmetric, then choices can be rationalized by an additively separable utility function. And the definition of additive separability, just to be clear, is given below. So in other words, we started with a, any rational and symmetric choice correspondence, which means any utility function that's symmetric. And then we added in what I've argued is a pretty mild computational constraint. And all of a sudden, we've got a very strong restriction on the functional form of the utility function corresponding to additive separability. What I want to do next is I want to tie this result back to the original framing that I gave you, which is about narrow choice bracketing.
Excuse me.
Yeah, please.
I'd like to ask a question. So when you emphasize symmetric here, what exactly do you mean and why it's important here? Could you explain to the audience? Thank you.
Yeah, so I'm just to be clear again about the definition, and then I'll sort of maybe give an intuition for what the role that it plays. So symmetry just says that if I replace xi with xj in the utility function, utility does not change, right? So it's this interchangeability of the coordinates of the outcome. And you can kind of see the role that it's playing through the following example. So actually, if you don't mind, let me answer the question now. I was thinking I might postpone by one slide, but let me just address it now.
It's okay if you are more comfortable to delay it. I'm just curious. What's role plays here?
I think it's a great question, and let me just address it right now. I think that's the best place. So okay, so if you think about the additively separable utility function, what's nice about it is that if you give me a product menu, right? So where the feasibility constraints are not like interlinked. If you give me a product menu, I can maximize expected utility just sort of one coordinate at a time. So I can just choose x1 to maximize u1, choose x2 to maximize x2, and so forth, because this utility function is separable. And that's going to correspond, as I'll mention on the next slide, to narrow choice bracketing, right? Like I focus on decision 1 without thinking about decision 2, without thinking about decision 3. And this is going to be without loss because my utility function is additively separable. However, you might think that there are other forms of choice that might also be tractable that are not additively separable. So for instance, suppose that I had a utility function, the first component of my utility function was u1 of x1 comma x2, right? And the second component was u2 of x3 comma x4, and then u2, u3 of x5 comma x6. So I have like pairs of coordinates that are separable from each other, but within each pair, the two coordinates might not necessarily be separable. This is going to look like choice bracketing that's not like one decision at a time, but two decisions at a time. And intuitively, that should also be tractable. And it also looks like choice bracketing, but it's not additively separable. So this result is not going to apply. And the reason why the result doesn't apply is because I assumed symmetry, right? So symmetry forces me, if I'm choice bracketing, symmetry forces me to bracket one decision at a time rather than, for instance, two decisions at a time. And so that's the sense in which it kind of simplifies things for my initial result. But of course, my more general result is going to get rid of the symmetry assumption and characterize what forms of choice bracketing we can see when things like, looking at two choices at a time are going to be allowed. Does that answer?
Basically, yeah, I get it. Basically, you're trying to simplify the assumption, but under such assumption, you're going to still get the conclusion of this bracketing as a rational choice.
Yeah, exactly. So it gives a simpler to state conclusion before I move on to the more complicated general result. Yeah.
Got it.
Yeah, thank you for the question. So,
sorry.
Yeah.
Previous slide. May I ask how much is your result of theorem 1 depend on the assumptions about the choice sets, the binary choices and the product choices? Because for me, I don't know, but for me, it's kind of very related to the choice set.
Yeah.
So for example, yeah.
Please go ahead. I didn't mean to.
Yeah, if we drop one assumption, say there's possibly not include all binary choices, what would happen to your theorem 1?
So that's a great question. So the first thing that, I think let me get back to the slides. So I think it's clear to you based on how you asked the question, but just to make sure it's clear for everyone. The assumption that I'm making is not that the decision maker is restricted to product menus with binary partial menus. It's that if the decision maker were presented with that kind of menu, they would be able to make a choice, right? Now you're asking, suppose that I even weaken the assumption to say that the decision maker does not need to make choices from all product menus with binary choices. That's how I understood you. So let me know if I misunderstood. So the answer is, I'm not sure. So I mean, certainly if you, I can give you a sense of like, if you like strengthen the assumption, if you add more kinds of menus in there, how the results might change. But if you even relax that assumption, I don't have a good sense. I think the main issue is I'm not sure what is like the
let me explain why I asked this question, because I try to somehow understand the intuition behind this theorem.
Yeah.
Why if choices are rational, tractable, and symmetric, then we can get a additively separable utility function, because that helps me to one way to get to that.
Right. Yeah. So I think maybe one thing that'll help is if I go on to the next slide. I'll just describe narrow choice bracketing a little bit more carefully, and
Sure.
then I'll sort of I'll make a point that it gets back at this question. So let me just briefly define narrow choice bracketing. So narrow choice bracketing on a product menu M is going to be a heuristic which optimizes over partial menus, MI, separately, right? So you like make one decision related to coordinate 1 of the outcome. You have some coordinate-specific utility function, U1 in this case, and then you maximize your expected utility according to that coordinate-specific utility, given all partial menus, partial lotteries in that partial menu, right? So it's like you focus on Alibaba shares without thinking about Apple shares, and you focus on Apple shares without thinking about Alibaba shares. Now, narrow choice bracketing can lead to all kinds of behaviors that we might think of as odd from a classical economic standpoint. Things like correlation neglect, things like small stakes risk aversion, but not the more large stakes risk aversion we're used to thinking of, sort of imperfect intertemporal substitution of things like labor supply, as we saw in the bike messenger example. So this leads to behaviors that you might think of as odd. But nonetheless, we can observe that on product menus, narrow choice bracketing is observationally equivalent to expected utility maximization with an additively separable utility function. So in that sense, when I told you that if choices are rational, tractable, and symmetric, then they can be rationalized by an additively separable utility function, I could have replaced that last line with, on a product menu, they are observationally equivalent to narrow choice bracketing. Now, okay, so let me get back to the question. So it's going to be hard for me to give like a complete intuition for like why the result is true without getting into the proof sketch. But let me say one thing, which is narrow choice bracketing is a heuristic that a decision maker could use. This heuristic is quick in the sense that you can run it in polynomial time. And you can run it in polynomial time. It will be without loss in the sense that like it will come up with the optimal choice as long as the utility function is additively separable and the menu is a product menu. So the heuristic of narrow choice bracketing is only well defined in a product menu. If you didn't have a product menu, if you had a menu where like the decision that I make, decision I, is going to affect what is feasible in decision J, then in order to make a feasible choice, I cannot fully narrowly bracket, right? So narrow choice bracketing as a heuristic, it's really only defined for product menus. Now, for product menus, if the utility function is, if and only if the utility function is additively separable, narrow choice bracketing will be without loss. The question is, what happens if the utility function is not additively separable? And it turns out that if the utility function is not additively separable, basically the best algorithm you can come up with is brute force search, where you search through all the possible lotteries. And again, because these lotteries are n-dimensional objects, this is going to require searching over a space of that is a set whose cardinality is growing exponentially with n. Now, the fact that if the utility function is not additively separable, or if narrow choice bracketing is not without loss, the fact that then there's nothing that you can do that's better than brute force search is not obvious, but that's kind of the substance of the theorem.
Yeah, I kind of got it. It's kind of like when you have a choice set, the choice per se should be separable. Say if two dimensions are not distinguishable, perhaps you will not got a additive separable U, kind of like that. But
Yeah,
it seems to me it's a necessary condition. Yeah. Okay.
it's a necessary condition.
Yeah.
Okay. Yeah. So additive separability is I guess a necessary condition for tractability in this model. Okay, cool. So let me see. Let me briefly just comment on the following, which is I just gave a result, theorem 1, that looked at the set of choice correspondences, imposed rationality, tractability, and symmetry, and told you what the result was, which was narrow choice bracketing. Now, I told you that I had a more general result that got rid of the symmetry assumption, that just characterizes this intersection, which corresponds to rational and tractable choice. Now, I don't and didn't expect to have time to really get into that more general result, but what I will mention is that I do have a characterization that describes the behaviors that are consistent with rationality and tractability without symmetry. And I can characterize this both in terms of a generalized form of choice bracketing that I call dynamic choice bracketing, and in terms of a generalized notion of additive separability that I call Hadwiger separability. But again, in the interest of time, let me move ahead, and I'm happy to talk a bit more about it afterwards. So if you don't mind, I'm going to take maybe 3 minutes of the question time just to make sure I'm able to highlight the final result. So the final result is about revisiting the normative appeal of the expected utility axioms. So let's think about a decision maker that cares about the expected value of some objective function u bar. An objective function is just like a utility function, except instead of something that's revealed through your behavior, it's something that you are intrinsically endowed with. Now, you'll note that by my previous results, not all of which I told you about, if the objective function is not suitably separable, then exact optimization is not tractable. And so if the decision maker is computationally constrained, they will not be able to exactly optimize. Nonetheless, we might suppose that the decision maker is, the decision maker still has to make decisions, right? They still have to make choices. And so they might look for choices that are at least approximately optimal. So the question I want to ask is, would an outside observer conclude that this decision maker that's trying to make approximately optimal choices is rational? So I'm going to need just 2 slides to give you that result. The first slide will tell you what do I mean by approximate optimality. Well, what I mean is the following. So I'm going to say that choices are alpha approximately optimal with respect to the true objective of the decision maker if for any given menu, the actual payoff that the decision maker gets is at least some fraction alpha of the optimal payoff. Okay? And this is sort of a common notion of approximate optimality used in computer science. I'm going to present it as one reasonable criterion that you might want to have. And as a reminder, I'm going to say that choices C are rational if they can be rationalized by preferences that satisfy the expected utility axioms. They can be rationalized even if they're not rationalized by the true objective function. So here's the final results. There exist objective functions, u bar, such that, first, no rational and tractable choices are even epsilon approximately optimal for any epsilon greater than 0. However, there exist tractable choices that guarantee you half of your optimal payoff. So in other words, if you insist on making choices that an outside observer will look at and say these are rationalizable, you will not be able to get guarantee any positive fraction of your optimal payoff. But if you're willing to make choices that are not rationalizable, you can actually get half of your optimal payoff guaranteed. So in that sense, the decision maker might be better off making choices that are not rationalizable. You might ask, for which objective functions is this true? Well, it turns out to be true for some very standard, common objective functions that reflect things like risk-averse preferences over wealth. Okay, so last slide. I'd like to summarize my results using the following diagram. I call this the choice trilemma. We began by introducing, defining rationality and tractability. And I characterized the intersection of rational and tractable choice as dynamic choice bracketing. Then I introduced approximate optimality. And we think about the intersection of tractability and approximate optimality as corresponding to what computer scientists call approximation algorithms. And then finally, we can talk about the intersection of rationality and approximate optimality. This set is a little bit less interesting to talk about, except the thing I want to point out is it includes the idea that the decision maker is exactly optimizing her true objective. And what my results show is that while you can guarantee any 2 of these 3 properties, you cannot guarantee all 3. And in particular, if you are computationally constrained, you have a choice to make, a meta choice. Do you want to make choices that are rationalizable or choices that are approximately optimal according to your true objective? And what I would argue is that you should make choices that are approximately optimal. Okay, that's it. Sorry to go a bit over time, but I'm happy to take any questions at this point.
Thank you so much for the terrific talks. Now we open the floor for questions and discussions.
Yeah, I would like to follow up with some questions, comments.
Yeah.
So firstly, I really appreciate your work. I think it's almost like a common sense that human beings have limited brain power in terms of thinking and memory.
Yeah.
So we have a lot of mental bias, and so I think it's common sense, but I think it's and there's been a lot of talk in the behavior economics, but I think it's nice to have a more general summary of understanding what's going on and have more general implications, because in behavior economics, we talk about a lot of different type of the bias, but it's not clear what's the common source, what's the common thing here. So I think it's really worthwhile. So firstly, I like the idea, and I think probably I would recommend that you spend more time to discuss the implications. Otherwise, people are not really going to get the much benefit. For example, you tell us, wow, because of the competing brain power, we have bounded rationality. Makes sense, but that's almost like a common sense. It's nice to prove it, but then I think you probably can discuss more. For example, I think you mentioned narrow framing, mental accounting, myopic loss aversion, choice bracketing, maybe, or there's also availability bias, and that's one of the most common thing in behaviors. So I think if you spend more time to discuss these things, and it becomes much more. So one suggestion is that you have a section, or you link clearly to the behavior bias and how they're related. That's one suggestion. The second thing is, I think you can link this to the common phenomena we observe in real life. For example, we see the in consumers, and so we see that it's very hard for consumers to remember anything. That's the whole idea of branding, positioning. So they only remember one brand or two brands. It's very hard for them to go through more why. So it's so fundamental, I think, for consumer behavior, and also for business decision makings. A lot of time talk about the big data, talk about a lot of things. I've observed multiple times that business executives, in the end, when they make the strategy decisions, it comes down to several factors, and they look at them to decide to bracket them into several dimensions to see, okay, this is going to be our strategy for this year, something like that. We're going to have 3 battles, this or that. So they always brackets. So I think that's my second suggestion. A better link and understanding with the behavior literature, and a better link to the important real life decision making and behaviors, and that would make the paper go far. And also, I would really encourage you to do more research along this line, because behavior finance, behavior economics is nice, but it's kind of I see it's kind of scattered a bunch.
Yeah, right. Well, thank you, Juan, for the kind words and all the suggestions. I fully agree. I think this paper, the way it came about is largely as a criticism of how we do decision theory. But I think, I mean, for me personally, the papers that will follow this one are the ones where I hope to have, more to say about, how we think about,
It's right now. It reads more like a mathematics paper, or the more theory and technical, but then it has rich intuition, and I think that part you should spend much more time. Maybe you can even write multiple papers, even a book on it. I think there's a lot to be gained from this.
Yeah, totally agree. Yeah. Thank you.
Okay, so let me address another question that I see from the chat. So the main body of our audience today are from the social science background and also the econ background. So they are pretty much interested in hearing about how computer scientists are going to think about the problem of time, right? So you talk about the reasonable time. So how do they interpret and understand the reasonable time? And could you make a brief summary between the two communities, between how econ people interpret this and how the CS people see this?
Okay, interesting. So what I would say is that, I mean, so the way that computer scientists think about time is the number of steps that an algorithm needs to take in order to, you know, spit out an answer. And in particular, the runtime, so again, the number of steps is not going to be sort of necessarily the same as like, I guess, chronological time or physical time. And one reason for this is because, you know, two different computers, let's say, right? One that, say, like a computer from the 1950s versus a computer from the 2050s, the same algorithm, they're going to have very different physical time, but still the same runtime. So, you know, even if to use human examples, someone who is very quick at processing might be able to run the same algorithm in a few seconds, and someone who's slow at processing might take a few minutes. So the way that computer scientists think about time or time complexity is really, how does the runtime scale as we increase the scale of the problem, right? So like as we increase the number of decisions, how quickly is the runtime blowing up? And the thing about sort of exponential blowups, like if the runtime is really growing exponentially with some parameter of the problem, like the number of products in a grocery store, then it kind of doesn't matter what machine you're running the algorithm on. Exponential growth is so aggressive that eventually you will run into problems. So, and of course, this is in sort of opposition to how economists think about time, which is mainly through like, you know, physical time and the idea of discounting and so forth. So what I think is a limitation of the paper that I presented, but an opportunity and something that I'm thinking about more generally for like future work at the intersection of economics and computer science, is how do we move beyond this notion of exponential versus polynomial time, right? Like how do we get to a notion of time complexity that's adapted to the scales at which humans are operating, right? For a human, adding two large numbers, as I mentioned, can be done in linear time in theory, but it can be quite challenging for human practice. Right. And so what I think is we want a notion of time complexity that sort of gets at the difference between, you know, adding two small numbers and adding two large numbers, right? Or the difference between running a logarithmic time algorithm or running a linear time algorithm. And I think there's a lot of interesting stuff to explore there. So that's a high level answer to the question. Let me know if I can add any more detail.
Hey, thank you. Thank you so much. This is a really good answer. And due to the time limit, I think we should stop here. Sorry for not able to accommodate any additional questions. And you're always feel free to send the follow-up questions to our email. And we have also sent our contact in the chat. If you hope to also receive any further updates, our weekly email address about the upcoming events, you're free to add us or email us directly. So thank you so much, Modibo, for today's fantastic talk. And thank you all of our audience for your participation. So
thank you so much.
You.
It's a pleasure.